In this circuit, we have the EMF, the voltage of the battery labeled, and we've also got the resistance of all the resistors. So we know everything we need to know about this circuit in order to figure out a whole bunch of other stuff. In particular, what information could we figure out based on the labels in the circuit so far?
The equivalent resistance?
Yeah, one thing is we could figure out the equivalent resistance, because if you ignore the battery, everything else is just a big clump of resistors. In fact, if you think of this as imagine all these resistors are in a box. If you don't see what's inside the box, all you see is a battery with a wire leading from the positive terminal into the box and a wire from the negative terminal into the box. If you run experiments on this without looking inside the box at all, then you'd be able to tell from the experiments that what's inside the box is a resistor. You might not know exactly how that's arranged inside the box, but the box is going to act like a resistor with a certain total amount of resistance. And that's only true because everything inside the box actually is resistors put together in various ways. If there had been something like a battery inside the box or a capacitor inside the box, it wouldn't act like just a resistor. But in this case, everything inside the box really is resistors, so we can treat that big box as if it was just one big resistor. And how would we figure out the total resistance of that whole cluster of resistors? What could we combine there?
3 and 4 in series, and then that's parallel with 2.
Yeah, it looks like resistors 3 and 4 are definitely in series because it's just one path. Resistor 3 and 4, if you trace along this path, in fact, any path you trace, any loop rule path is going to go through resistor 3 and resistor 4, or neither one. For instance, if you draw a path through the battery, it's possible to go through neither resistor 3 nor resistor 4. And it's also possible to go through resistor 3 and resistor 4. But there's no way you can draw a path that includes resistor 3 and not resistor 4. And there's no way you can draw a path that includes resistor 4 and not resistor 3. It's either both of them or neither of them. That's one way to interpret series. 2 resistors or more are in series if any path goes through either all of them or none of them. So we can definitely say 3 and 4 are in series, and they're going to act like how much resistance in total?
12 ohms.
Yeah, since they're in series, we can just add the resistances. 3 and 4 together act like a single 12 ohm resistor. So let's combine those.
If we were to write out the loop rules, we would have 2 of them.
You could actually do 3, and that is one option. Instead of combining the resistors, you could just write out loop rules equations. So one possibility, instead of drawing out the equivalent resistance, you could write out loop rules. You could have a loop through the battery, resistor 1, resistor 2, and resistor 5. Those delta voltages would have to add up to 0. And you could have a loop through the battery and resistor 3 and resistor 4 and resistor 5. Those voltages have to add up to 0. And also you could even have a loop through resistor 3, resistor 4, and resistor 2. Those voltages have to add up to 0. So you could use the loop rule to write out 3 equations. And what would be the unknowns in those equations?
The currents.
Yeah, the currents. And it looks like we have, how many unknown currents do we have here?
3.
Yeah, it looks like 3, because we've got current through the battery, which we usually call I sub 0. The blue loop, let me pull that back up.
For the blue loop with 2, 3, and 4, so that would just be minus IR minus IR minus my IR equals 0?
Yes, except for one thing. Loop has a directionality associated with it. But in resistor 2, which direction would you expect current to be actually flowing?
Oh, the opposite direction.
Yeah. So we've got, let's say, current 2 flowing downwards and current 3 flowing to the right and downwards and to the left. The direction of the current, typically you just guess. If you know which region is higher voltage and which region is lower voltage, you can expect current to flow from the higher voltage region towards the lower voltage region. But if you're not sure, you can just guess a direction for the current. And we're essentially picking a direction to call positive in terms of the current. If it turns out the current is actually flowing the opposite direction, that's fine. You'll just get a negative value for current. So if you're solving for current and you find that the current is a negative value, that just tells you the current is actually flowing in the opposite direction from what you thought. And that's fine. That's just how you know the direction of current at the end. In this case, though, our loop, the blue arrows I've drawn here in this loop, they're going with the direction we're choosing for current for resistors 3 and 4. So we'll have plus negative IR, plus negative IR. But since it's going in the opposite direction for resistor 2, we'll have plus positive IR instead. So we just treat it as the opposite sign. Or alternatively, you could still write it as negative IR. It's just that current will be negative I2 instead of I2. So that loop rule would look like delta V for resistor 3 plus delta V for resistor 4 plus delta V for resistor 2 equals 0. But if we actually wrote out those delta V's, for resistor 3, we'd have negative I3 times 7 ohms. For resistor 4, we'd have negative also I3 times 5 ohms, because it's the same current since they're in series. And for resistor 2, we'd have negative I2 times 8 ohms. Because our loop is going through resistor 2 backwards, compared to the current. So we treat the current, we still write it as negative IR. We just treat the current as negative I2. Those negatives cancel out, so it becomes plus I2 times 8 ohms. So overall, our equation is going to turn into negative 7 ohms times I3 plus negative 5 ohms times I3. And those can be combined into just negative 12 ohms times I3 plus 8 ohms times I2 equals 0. So that at least gives us an equation relating I3 and I2. You could also draw out other loop rules to get more equations relating I1, I2, and I3. Let's say I1 is the current through the battery. And as long as you can get at least 3 equations relating those 3 unknowns, then that's enough information to solve that system of equations. So one way of analyzing a circuit is to write out all the loop rules and possibly junction rules you can. And that gives you a system of equations. As long as you have as many equations as you have unknowns, that's a system of equations that can be solved using substitution or elimination or matrices or any other technique from any math class. However, that's usually not the fastest or most efficient way of analyzing a circuit. It's always possible as long as you can write as many equations as you have unknowns. But typically there are easier methods involving combining the resistors and sort of mapping out the voltages instead. So you certainly can set up a system of equations and solve it. In some complicated circuits, especially with multiple batteries or weird arrangements of resistors, that might be the only way to do it. But let's take a look at a simpler method of analyzing this particular circuit. Instead of drawing out a bunch of loop rules, let's go ahead and simplify the resistors so we can treat them as just one big resistor. You mentioned earlier that 3 and 4 can be combined into just 12 ohms, so let's do that. 3 and 4 we can combine and say they act like a single 12 ohm resistor. So let's call this R34, which is 12 ohms. And then what else can we combine here? Is there anything else that's in series before we move on?
No.
There is one pair that's in series. Yeah, 1 and 5. How can you tell that resistors 1 and 5 are in series with each other?
If you pass through one, you have to pass through the other.
Exactly. By definition, any path is going to pass through R5 and R1, or neither one. There's no way you can draw a path that passes through R1 but not R5. And yeah, it's also just one path. These are on the same single path. There's no other junctions between them. The presence of the battery doesn't change the fact that they're in series. So R1 and R5 can be added together. They can act like one single resistor. So let's combine those. R1, 3 ohms, R5, 2 ohms. So we can add those and say they act like just a single, wait, what was that? 3 and 2, so that'd be 5 ohms. So let's call that R15. R15 is 5 ohms. So we'll combine that into one equivalent resistor. And at this point, it looks like we've done everything we can with series so far. What else can we combine in parallel? It doesn't actually matter where you place it as long as it's along this path, because anything in series, you're just going to be adding things together anyway, and addition is commutative. Order doesn't matter. So if we had put it on the other side, or if we had just rearranged R1, R5, and R1, R5 in the battery, the order does not matter one bit. And yeah, R34 is in parallel with R2 because those are just alternate paths. They both start at the same region and they both end at the same region. So how would we combine those? How do you add things together in parallel?
1/12 plus 1/8, and then take the inverse of that.
Yeah, 1 over you add up the inverses, that equals 1 over the equivalent resistance. And how would you add 1/12 plus 1/8? Yeah, you could also combine R2 with R34 and then say that's in series with R1 and R5. Or you could combine R1 and R5 first. Either way works. So there's often many different ways to get to the final result. To add 1/12 and 1/8, what's a common denominator there?
24.
Yeah, if we just multiply the first one by 3 over 3, and the second one by, 2 over 2, and then 3 over 3. So 5/24, then invert that, we get 24/5. Or as a decimal, that would be 4 4/5, so 4.8. So that means all these together are 2, 3, and 4 act like 4.8. So let's go ahead and combine those. And say R2, 3, and 4 together act like 4.8 ohms. And then what's left, R15 and R2, 3, 4 are just in series because there's just one path. So how do we combine those?
Add them.
Yeah, add them up, and we can say this whole thing acts like just a 9.8 ohm resistor. So this entire circuit acts like a battery connected to a single 9.8 ohm resistor as far as the mystery box is concerned. If we have all the resistors enclosed in a mystery box and we're not allowed to look inside, any experiment we can do from outside will reveal that the box acts like a single 9.8 ohm resistor. And of course, what's actually going on inside could vary depending on how the current splits up. But any experiment from outside the box will suggest this acts like a 9.8 ohm resistor. And in this simplified circuit, now that we've just got one battery and one resistor, the loop rule is going to be very easy to write. We just got delta V from that one battery plus delta V from the equivalent resistance equals 0, because we've got a complete loop. If we fill in the values there, we know that epsilon for this battery is 98 volts plus negative IR, I times 9.8 ohms. And how would we solve that for I? How would you isolate I in this equation? Yeah, 98 divided by 9.8. So 98 volts divided by 9.8 ohms. That'll be 10. And then volts over ohms is amps. So that means the current in this simplified circuit is 10 amps. Any questions on that so far? And now if we go back to the original circuit, the one we actually care about before simplifying it, in the original circuit, that 10 amps is actually the current in what part of the circuit?
The first part, I1.
Yeah, because, well, specifically the current through which element, which thing?
Through the battery.
Yeah.
So also 1 and 5.
Exactly. The battery is the one thing we didn't simplify. So the current we just found, 10 amps, is specifically the current through that battery. And yeah, it also happens to be the current through resistors 1 and 5 because they're in series with the battery. So let's fill that in. We know for sure that this current through the battery and R1 and R5, that is a 10 amp current. Let's go ahead and call that I1. I1 is 10 amps. We know that for certain. When it hits the junction, of course, it's going to split up. And we'll need to know how it splits up. So let's say we call those I1 or I2 and I3. I2 and I3. So I2 and I3, we don't know yet. But what do we know about how they're related to each other?
They add up to I1?
Yeah, from the junction rule, just looking at either of the junctions really, let's say this one, the current in is I2 plus I3, the current out is I1. So we know for sure that I1 equals I2 plus I3, current in equals current out. In other words, I2 plus I3 has to add up to 10 amps. But that alone doesn't tell us how it splits up. And there are several ways for figuring out exactly how it splits up. I think one of the best ways in cases like this, or in terms of most universal application, is to start looking at the voltages. One way to do this is the loop rule, but I think a much more visual approach is to start mapping out the voltages everywhere. Like for instance, we're going to need a location to call 0 just as a reference point. What do you think would be the best location in this circuit to call 0 volts?
Like right before the battery, that corner maybe?
Yeah, if we take a look at this corner on the negative terminal of the battery, since it's the negative terminal of the battery, this is presumably going to be the lowest voltage in the whole system. So let's call that 0, and then everything else will be some amount above 0. So this voltage we'll call 0 volts. And then we can also label the other regions. So essentially, the idea, we usually call this idea nodes. A node, like this blue corner would be a node. A node is just a region of points that are all connected by just wire with no batteries or resistors or capacitors interrupting it. So how many nodes do we have in this circuit? How many different regions of just wire do we have?
5.
Yeah, I think so, because we have the points on the negative terminal of the battery. We have this corner on the positive terminal of the battery. That's got a different voltage because we're going through the battery. Across resistor 1, we have another region that's got its own voltage. So this sort of T-shaped region would be another node, a collection of points connected by just wire. And then across R3, we've got another corner. So this corner would have its own value of voltage. This node has its own voltage. Across R4, we've got one more region, which is, I'm kind of running out of colors here. Let's say this region here would also be a node, all these points connected by just wire. So it looks like there's 5 different nodes in this circuit. Each one of those nodes is going to have its own voltage. We're assigning 0 volts as a reference point to this lower left corner, the negative terminal of the battery. When you cross over the battery, what's the new voltage in this upper left node?
98 volts.
Yeah, the whole point of a battery is it creates a constant difference in voltage. Batteries don't really directly do anything with current. They just have a voltage difference. that voltage difference causes current to flow through the resistors, but I would say the current is more associated with the resistors. Why wouldn't the wire after R2, this region here?
Yes.
The region below R2 and the region like below R4, those regions are connected by just wire. Any locations connected by just wire with no resistors or batteries or capacitors interrupting it all have to be at the same voltage, because wire links locations that have the same voltage. So all these locations on the wire here, all these ones I've marked in pink highlighter, are essentially just one location because they all have the same voltage.
Thank you.
Mm-hmm. In fact, you could even redraw the circuit diagram, treating each node as if it were just a single point. If we just have the 0 volt node and then the 98 volt node, if we just draw each of these nodes as a single point, we could redraw the circuit as just wires linking those points together. So if we just draw each node as a single point, we can then consider what's connecting those nodes. For example, from this lower left node to the upper right node, we've got a battery and that's it. Then from orange node to green node, we've got a resistor and that's it. From green to purple, we've got a resistor and that's it. From purple to pink, we've got a resistor, specifically R4. From green to pink, we've got a resistor, R2. And from pink to blue, we've got a resistor, R5. So this is an exact replica of the exact same circuit. You could move these points around wherever you want. It doesn't matter what shape the wires are, doesn't matter where things are. All that matters is what's connected to what. So you can treat each of these nodes as if they were a single point, because any locations that are all at the same voltage are essentially the same locations anyway. Any questions on that redrawing so far? And redrawing circuits can often be very useful. If you've got a circuit that's kind of difficult to see what's going on, sometimes redrawing it with different shapes, but keeping everything connected in the same way, can make it easier to see what's going on. In this case, though, I think we can just stick with the original diagram. The important thing is we've split it up into nodes. Each one of those nodes should have its own voltage value. We're starting by assuming the lower left is called 0, just as a convenient reference point. And then you go through the battery that adds 98 volts. So we're now at positive 98 volts. So this entire upper left corner is at a voltage of 98. Then we go through resistor 1. And what should we expect to happen to the voltage?
It should drop.
Yeah, it should drop. And how can we calculate how much it drops?
The delta V minus IR.
Yeah, delta V for a resistor is minus IR. We know the current in this section of the wire. We know the resistance, so we can multiply those to get how much voltage drop.
30 volts.
Yeah, exactly. Delta V equals negative 30 volts. So for this resistor number 1, we are losing 30 volts. From 98, we subtract 30, we end up with 68. So that means this green region, this top middle node is 98 minus 30, so 68 volts. 68 volts. The loop rule, delta V loop equals 0. The epsilon minus IR is if you're talking about one battery and one resistor. So for instance, in the simplified version, when we just had one battery and one resistor and that's it. If your entire loop is one battery and one resistor, then the delta voltage for the loop is epsilon minus IR, which equals 0. But that's only if you're dealing with exactly one battery and exactly one resistor. More generally, I would say the more useful formulas are delta V for any battery is always going to be plus epsilon. Let me actually go get an epsilon 1 moment. Epsilon, there it is. Delta V for a battery will be always plus epsilon, where epsilon is just some constant associated with the battery. Delta V for a resistor will always be negative current times resistance. And when we get to capacitors, delta V for a capacitor will always be negative charge over capacitance. Q being the charge stored on the capacitor right now, and C being the capacitance, which is a measure of the efficiency of the capacitor. So these, I think, would be the best formulas to use. If you're dealing with a battery, it's delta voltages plus some constant. If you're dealing with a resistor, it's delta voltage from one end to the other is negative current times resistance. In this case, we know the current, we know the resistance, so we can multiply those to find the voltage drop. So we know this top middle node is 68 volts. Any other questions on that so far? And then for R3 and R2, we don't know the current yet, so we can't really figure out the voltage drop. So we're kind of at a dead end there so far. But if we backtrack, we also know resistor 5's resistance and current. So what's the negative 30 was from finding the delta V for the resistor. Delta V for any resistor is always going to be negative current times resistance. For resistor number 1, we know the resistance and we know the current. So we can multiply them to find what's the difference in voltage across that resistor. 10 times 3 would be 30 with a negative, so negative 30 volts. That means as we pass across this resistor, comparing one end into the other, those two ends have a difference of negative 30 volts. So from the 98 volts we started with, we lose 30 volts and we end up with 68 volts left. So this region has a voltage, the electrical push, equal to 68 volts. But we can't really go anywhere from there because we don't know the currents through resistors 3 or 2 yet. But if we backtrack, we do know the current and resistance of resistor 5. So what would be the delta voltage for resistor 5? Yeah,
20.
multiply negative current times resistance, 10 times 2. So delta V is negative 20 volts for resistor number 5. That means in the direction current's flowing, we started at some high voltage, we lose 20 volts, we end at 0 volts. So what was that high voltage we started at? Yeah, had to have been 20 also, because 20 minus 20 gets us back to 0. So this entire pink highlighted region in the lower right is going to be at 20 volts. And we now know how much voltage resistor 2 is dropping. Resistor 2 starts at a 68 volt zone, ends at a 20 volt zone. So that tells us what's the delta voltage for resistor 2. Yeah, that's got to be 48. Looking at resistor 2, we can say, as usual, delta V equals negative I times R. We know delta V is negative 48 volts because we start at 68, we end at 20. So the difference is negative 48 equals negative I2, which we don't know, times resistance, which is 8 ohms. So how would we solve for current 2 here? Yeah, or more formally, I would say divide by negative 8 because we want to cancel out that negative also. So negative 48 divided by negative 8 is going to be 6. So that means the current through resistor 2 is 6 amps. We now know that current. And if we know current 2, what else can we immediately find?
Current through 3 and 4.
Yeah, because those currents are related by the junction rule that we were looking at earlier. We know that current 2 plus current 3 must equal current 1 because of the junction rule. We now know current 2. So what does current 3 have to be?
4.
Yeah, current 3 has to be 4 amps according to the junction rule. which also means as one, I mean, we now know all the currents, but just as one final check, we can also find the voltage of this one missing node at the top right. If we're assuming we now know that the current is 4 amps. And the resistance is 7 ohms for resistor 3. Multiply those, and what do you get?
28.
Yeah, so delta V for resistor 3 is negative 28 volts. Which means if we start at 68 volts and we lose 28 volts, we're left with 40 volts. So this upper right node is at a voltage of 40 volts. And then one last transition. We've got 4 amps of current flowing through a 5 ohm resistor. So what's the voltage drop there?
20.
And if we start at 40 and we lose 20, we end up with 20, which exactly matches what we got here. Then we lose another 20, you end up with 0. So we now know the voltage at every node and the current in every path. That's really the main goal of circuit analysis. Assuming you know the voltage of the battery and the resistance of every resistor, look at it in terms of labeling the paths with unknown currents and labeling the nodes, these locations, with unknown voltages. If you can find the current in every path and the voltage at every node, then you know everything you need to know about the current or about the circuit. You can also, if you need to, find power by using any of the power formulas, because the power formulas involve current, voltage, resistance, any 2 of those 3. Every power formula is 2 of those 3 things, current, voltage, and resistance. So for any resistor, if you know 2 of those things, you can immediately find the power before you even need to find the third one. Like as soon as we knew that the voltage drop for resistor 2 was from 68 to 20, that's minus 48 volts, you could immediately use voltage squared divided by resistance to find the power of resistor 2 before you even calculated the current. So as soon as you know any 2 of voltage, current, resistance, you can immediately calculate the power dissipated by that resistor. Any other questions on that example so far?
If we were to like lose a circuit, or sorry, lose like a resistor or have it burn out or something, would we need to reanalyze the entire circuit?
Yes, because everything could change. The only thing that wouldn't really change if a resistor changes is if you've got some resistor that's in parallel with the battery directly. Like for instance, if we had another resistor that was, let's say, like this. The presence of this resistor does not influence the rest of the circuit at all. And the rest of the circuit does not influence this resistor at all. Since this resistor, no matter what's happening with the rest of the circuit, how much voltage is this new resistor getting?
The entire battery?
Yeah, this resistor is getting the full 98 volts from the battery. So this resistor is not influenced by the other resistors. No matter what's happening with the rest of the circuit, this resistor is getting a full 98 volts. So its current will be the same it always is, no matter what happens with the rest of the circuit.
Okay, and that's only in the case that it's by itself connected to the positive and the negative end of a battery?
Yeah, because that means that this branch is getting the full epsilon of the battery, no matter what happens with the rest. Even if we have like a burnout that, or if we just unplug this and leave it open, so no current at all would flow through the rest of the circuit, but this branch is still getting the full 98 volts of the battery. Or if we put in, let's say, a short circuit that bypasses resistor 1, resistor 1 would get nothing at all because there's no longer a voltage difference. We're combining those nodes, and everything else would probably get a little bit brighter because now there's less resistance. But this resistor is not influenced at all because it's still getting the same 98 volts from the battery. I3 and I4 have to get the same current because they're in series. So any path through resistor 3 also passes through resistor 4. Change in V for R2. For that one, we subtracted. We figured out the node at the top has 68 volts. The node at the bottom has 20 volts. So we calculated those separately, and then we can just take the difference. If you think of it as final minus initial, 20 minus 68 is negative 48. So if you pass through resistor 2, you're losing 48 volts in terms of the difference from start to finish. Any other questions on this circuit? Then let me pull up one more. I'd like to take a look specifically at one of the problem starts. I think it is number 2. Let me pull that up. Not to work it out in full because it doesn't have any numbers assigned to it anyway. So for this one, it can be kind of difficult to see what's in series and what's in parallel. I'm not going to run through the whole analysis here because we don't really have any numbers attached to these and we're kind of short on time anyway. But just to get an idea of how we would combine these and how to figure out whether they're in series or parallel or whatever, I would recommend looking at it in terms of nodes again. Like in the previous one, we were looking at like this entire region is all at the same voltage. So we'd call that a node. This region connected by wire is all at the same voltage. So we'd call that a node. So if we mark off the nodes the same way we were doing before, let's say we start with a point right before the battery, because that's going to be the lowest voltage. We'll just call that 0 volts. What other locations are going to be the same voltage as that location? Or how would we find the other locations that are the same voltage?
Would it be like after R1 and then before R3 and before R5 and 4?
Yeah, because if you imagine that the property of having 0 volts sort of spreading out along wire, all these locations connected by wire, all these locations are going to be at the same voltage, which we could call 0 volts. So this would be a node. And let's call that node A, or location A. And then, of course, when you pass through the battery, you're gaining some voltage. So this is going to be a different voltage. This region, I'm going to make that a different color. This region is a different color. But note that as soon as we hit a resistor, the voltage is going to change again. So this node is pretty small. So this would be node, let's call that node B. Then when we cross over R2, we get a different voltage. Let's call this node C. And how far does that node spread in terms of all points with that voltage?
The rest of the circuit, basically.
Yeah, all the rest of the circuit is connected to that. Because if we imagine this location, if we spread that out through all points that are connected by wire, that's all the points up here. Those are all at the same voltage. They're all part of node C. And all these points and these, that's all one node. All of these locations I've just marked in green down here are all at the same voltage. This entire circuit really has only 3 nodes, node A, node B, and node C. Which means one way we could write this out is, or we could redraw the circuit by treating each one of those nodes as a single point. So let's say we've got node A, and we'll make it bigger, node A, and node B. And node C. And we could put these in whatever arrangement, whatever shape we want. Because again, the shape of the wires doesn't matter. All that matters is what's connected to what else. So if we wanted to use these to draw, let's say we just arrange these in a triangular shape, what connects node A to node B?
Battery.
2 resistors.
Yeah, the battery and I guess just the battery, right? Because if you're looking at node A and node B, the only way to get from node A to node B is by going through the battery. So from node A to node B, the only connector is the battery. Let me put that in black for clarity. So from node A to node B, the only connection is the battery. What about from node B to node C?
Resistor 2?
Yeah, resistor 2 is the only connection between node B and node C. Like if you're at node B, the only way to get to node C is by going through R2. At least the only way to get directly to node C. You could take the long way around through node A, but the only connector from node B directly to node C is resistor 2. What about the connectors from A to C?
R3, 4, and 5.
R3, 4, and 5, and also what else?
Oh, 1.
Yeah, R1 is also a connector from node A to node C. So that means all 4 of those are going to be connectors from A to C. R1, R3, R4, and R5. What does that tell you about how R1, R3, R4, and R5 are connected?
They're all in parallel.
Yeah, those are all in parallel. So it might be convenient to redraw this circuit, again, keeping in mind that the shape doesn't matter. All that matters is the connections. You could say we've got a battery. You've got resistor 2. And then 4 more resistors in parallel.
Does it matter that the placement of R2 is like on the same strand as the battery? And so there's like
it does not matter, in fact. We could treat the resistor 2 as up here, right? It doesn't have to be on the same path, yes. But it doesn't matter which side it's on, is what I'm saying. You could put resistor 2 before or after the battery. All that matters is it's on the same single path as the battery. So this circuit, if we have resistors, I guess that would be resistor 2, and then 1, 3, 4, and 5. This circuit and this circuit and this circuit, all 3 of these diagrams are describing the exact same circuit. They're just different ways of drawing it. So there's often many, many different ways to draw the same circuit, as long as you're keeping track of what's connected to what. For instance, if we label these nodes in the same way, node B was between the battery and resistor 2, and then node C was between resistor 2 and the rest of the resistors. And then node A was between the negative terminal of the battery and all these other resistors. So exact same circuit, exact same nodes, all those nodes will have the same voltage as they did in the previous diagrams, because these are all describing the same physical situation. The only difference is the shape we're drawing it with, but again, the important thing is the connections. So in any circuit, I would say it's a good idea to start by thinking about it in terms of what are the nodes, what currents do we have? If you can label all the nodes and label all the currents with variables, even if you don't know what they are yet, then that's a very good step on the way towards analyzing the circuit. You now at least have a consistent notation that you can use to describe everything. Like for instance, you can say resistor 3 is a bridge from node A to node C. So it's got to have the same delta voltage as any other resistor that links from node A to node C.
I was just going to ask, so the only thing we can really conclude from this problem start without any numbers is that delta V1 equals delta V3 equals delta V4 equals delta V5.
That is definitely true, yes. We know those 4 resistors have to have the same delta V because they're in parallel, because they're all bridges from node A to node C in some way. And I think redrawing it like this makes it a lot more clear. Oh yeah, these are definitely in parallel. They've all got to have the same voltage drop because they all start at the same high voltage and all end at the same low voltage. I guess C would be the high voltage, A would be the low voltage. Any other questions on that? Yeah, go ahead.
Sorry. Oh, I was just, so in terms of current with 1, 3, 4, and 5, it constantly splits. So 1 and 3 split, and then the current splits again from 3 and 4, and then splits again from 3 and 5, or is it simpler?
Sort of, but you could also look at it in terms of nodes. We could just say, because the current within a node doesn't really matter. All we really care about is the current through any given resistor. So if we look at this in terms of current in the, let's say this sort of triangular diagram, we've got current through the battery. We've got current through resistor 2. I guess that'd be the same current. Through the battery and resistor 2 are going to have the same current because they're in series. But then that splits up into possibly 4 different currents. Let's say this current and this current and this current and this current. So we could have 4 different currents, I guess current 1, current 3, current 4, current 5 has to add up to the current through the battery in R2 because of the junction rule. But how it splits up depends on the resistances. If all these resistances are the same, then it's going to split up equally. If they're different resistances, then whichever one has the smallest resistance gets the most of the current. Whichever one has the largest resistance gets the least of the current. But they do have to add up to the current through the battery in this case.
So if we were to, oh, sorry. No, I was just gonna say, if we were to write the I total equals and then apply the junction rule, we would have 5 different terms.
Yeah, we would say, for instance, if we call this current, and let's say current 2, because it is the current through resistor 2, I2 equals I1 plus I3 plus I4 plus I5. But you could use the simplified resistor if you combine it all into one equivalent resistance to figure out the current through the battery, then use that to find the voltage drop across R2, and then figure out the difference in voltage between node C and node A. Use that delta voltage to find all 4 of these other currents, and then verify that they really add up to the current through the battery. All right, I've got to get going, but try using this same approach, this idea of simplifying the circuit, mapping out the voltage, maybe even redrawing it using the nodes approach. Try out some other examples. If you want some more practice problems, I've got a whole worksheet of other circuits to try out on math.anshees.org. So take a look there when you get a chance. Let me know if you have any other questions, and I will see you next time.